Cylindrical coordinates and spherical polar coordinates were invented to help solve math problems that would be difficult or impossible to solve using Cartesian coordinates. The problem, though, is that they involve lots and lots of formulas. Here are a few of them. Trying to remember all of these is a bad idea, and looking them up is a headache. The good news is you don't need to do either of those things. All you need to do is to know basic trigonometry and to remember two triangles. Here they are. And you really should have some experience using polar coordinates in 2 dimensions as well. I'm going to be using these two triangles to derive all of those formulas. There are lots of other formulas you can get as well that I won't be getting into, including a bunch of calculus formulas. If anyone would like to see more videos on stuff like that, let me know in the comments and I'll look into it. So here we have 4 coordinate systems. Cartesian coordinates, x, y, z, polar coordinates, r and theta, cylindrical coordinates, r, theta, z, and spherical polar coordinates, rho, theta, phi. Now, all of these variables are consistent. So this z is the same as this z, this r is the same as that r, this theta is the same as this theta, which is the same as that theta, and x, y, rho, and phi are all distinct. Now, cylindrical coordinates are pretty easy. If you know polar coordinates, all you really have to do is add a z. The really interesting and challenging one is going to be the spherical polar coordinates. In polar coordinates, theta looks like this. So in cylindrical coordinates, theta looks like this. And in spherical polar coordinates, theta looks like this. Theta is similar to longitude on a globe, while phi is similar to latitude, and rho is similar to elevation. Now, before we move on, we need to deal with an annoying technicality, which is that the choice of variables for cylindrical and spherical polar coordinates have not been standardized. Different textbooks use different variables. These are the variables I'm going to be using going forward, and they're the variables that are used in several popular calculus textbooks. Unfortunately, there are many other variations out there. For example, sometimes you see this, which is annoying because this r is the same as this rho, but this r is not the same as this r over here. Now you can avoid some confusion if you just change this r into a rho. And now these two are consistent, but you still have a problem where this rho is a match for this r, but this r is not a match for that r. And there's another one. How about we switch up the theta and the phi? This last pair is used in a lot of physics textbooks, but there are a lot of variations out there. Again, we have a situation where these two are consistent with one another, but this phi corresponds to this theta, and this theta has nothing to do with that theta. So before you can make use of what I'm going to show you, you need to double check your textbook or your class notes to see what variables they're using and how exactly those variables have been defined. And that's something you should know anyway. And if they are not an exact match for what I'm doing here, then you need to figure out how to compensate. Here we have a coordinate, xy. There's x and there's y. The distance from the point back to the origin is r. We define theta to be the angle between r and the positive x-axis. This is just polar coordinates in 2 dimensions. And we can write several formulas just looking at this. For example, there's the Pythagorean theorem. We can also do a bit of trigonometry. So tangent theta is opposite over hypotenuse, which is y over x. Cosine theta is adjacent over hypotenuse, which is x over r. but we usually write it this way. And not surprisingly, y is equal to r sine theta. If someone gives you values for x and y, you can use the first two formulas to calculate r and theta. If they give you r and theta, you can use these two formulas to calculate x and y. From polar coordinates, we can go directly to cylindrical coordinates. I'll make this my x-axis and this my y-axis. So here's my triangle with x, y, r, theta, and the right angle. But now we need a third dimension, which is why we have the z-axis. So if you go straight up from here, that distance will be z. And r and z actually form a plane. And the coordinate will be r, theta, z. Now the conversion formulas are identical to what we have here. So if you know polar coordinates, then you've already got cylindrical coordinates in the bag. There's only one possible point of confusion, which is, what's z? We've got formulas for x and y, so what's the formula for z? It's pretty easy. It's just z, because z is the same variable in both coordinate systems. So let's see about spherical polar coordinates. I'll start out by drawing the same stuff I had before. I'll change the color of r to blue. Now z is perpendicular to the xy plane, so we'll have a right angle in there. So now I'll draw these again. There's my r, there's my z. We can make a triangle out of this. There it is. On this graph over here, this hypotenuse looks like this. We can give a name to this hypotenuse, call it rho. And now we need to define an angle. We could go with this, but everyone goes with this. So we'll call that phi. Incidentally, the angle up here is the same as the angle down here, which is the angle between rho and the z-axis. And there it is, right there. When rho equals 0, you're just right on the positive z-axis. So if this is my z-axis and this is my rho, the angle between them can be anything from 0 to 180 degrees. At 0 degrees, you're on the positive z-axis. At 180, you're on the negative z-axis. At 90 degrees, you're somewhere in the xy plane. And you can actually rotate around in any direction to cover the entire xy plane. Now, at other angles, it's a little hard to visualize. Imagine if phi is about 45 degrees. If you rotate around to different theta values, all of the possible points that have the same phi value will make a cone shape. Once we've got our triangle set up, we can do exactly what we did up here. We can write 4 equations. Here's the first one, the Pythagorean theorem. Tangent of phi is opposite over adjacent, which is r over z. And then sine and cosine will get us these two. And of course, you can write theta equals theta, since theta is the one variable the two coordinate systems have in common. So these equations show us how to convert between Cartesian and cylindrical coordinates. These show us how to convert between cylindrical and spherical polar coordinates. So the obvious question is, how do we convert between Cartesian and spherical polar coordinates? X is equal to r cosine theta, but r is equal to rho sine phi. So x is equal to rho sine phi times cosine theta, where rho sine phi is simply equal to r. In a similar fashion, y is equal to r sine theta, so y equals r sine theta. And then z is just equal to rho cosine phi, which we already knew. So if someone gives you rho, phi, and theta, you can use these three formulas to calculate x, y, and z. What if someone gives you x, y, and z and you want to calculate rho, phi, and theta? Well, rho squared is equal to r squared plus z squared, but r squared is equal to x squared plus y squared. So rho squared is equal to x squared plus y squared plus z squared. Tangent phi is equal to r over z. So tangent phi equals r over z, but r, or r squared, is equal to x squared plus y squared. So if we take the square root, then the radical is simply r, and now we have r over z. Last but not least, tangent theta is simply equal to y over x. Now I highlighted these two in blue just to remind you that they are redundant. This z we already have over there, and this we already have up there. So if you're going to write these down on a note card, you really only need to write down the black stuff. Thank you very much for watching. Please like and subscribe. Also, if you would like to be tutored online by me personally, I am available. There's my website, alternaprof.com, and there's a link to that in the description down below.